Hello, I'm Professor Afshar at Glendale Community College. This is Physics 101, lecture 48. In this lecture, we'll discuss elastic deformations. This topic is covered in chapter 12 of our textbook by Survey and Jouet. We began this semester by studying the motion of point particles. A point particle is an idealization that serves as a good model for an electron or an atom or maybe a molecule, for example. Gradually, as we learned more physics, we began to consider rigid bodies. A rigid body is essentially a collection of point particles that better resembles the everyday objects that we encounter, like airplanes and chairs. We sometimes refer to these rigid bodies as extended bodies, but we always treated them as rigid, meaning that their shape did not change. The basic geometry of the object we were considering would not change as it moved through space. As it turns out, this is only an approximation. No object is perfectly rigid. An object will deform under sufficient force. Even a block of concrete or steel would deform if enough of a force is applied to it. In this lecture, we want to understand deformations a little bit better. We want to understand how objects stretch and bend, how they change their geometry in response to forces. To understand deformations, we need to recognize that in general, deformations depend on at least four important parameters. The magnitude of the applied force is important. Obviously, a small force of 10 or 20 newtons is not really going to deform a block of steel, but a much larger force would have a noticeable effect. The direction of the applied force is also important. If you have a rod of steel, for example, and you pull on this rod in one direction, you could stretch it. If you apply the force in the opposite direction, you could compress it. If you apply the force perpendicular to the rod, you could bend it. Each one of these is considered a deformation, a changing of the shape, and which type of deformation we have depends on the direction of the force that was applied to the rod. The material or substance of the object is obviously very important as well. Some materials deform more easily than others. For example, rubber deforms much more easily than steel. The geometry or shape of the object is also important. The way a cubical block of steel deforms is different than the way a cylindrical piece of steel would deform. So if we're going to discuss the deformation of steel, we need to know the initial geometry of the object that we're discussing. Now, in general, there are many different ways that an arbitrary object can deform. In this class, we'll study three specific types of deformations. There are certainly other types, but those other types often resemble these three main types of deformations. We'll be discussing tensile deformations. Roughly speaking, a tensile deformation is a stretching of the object. We'll also discuss shear deformations. Roughly speaking, the shearing of an object refers to the shifting of different faces of the object relative to each other. And we'll also discuss bulk deformations, in which an object is compressed, thereby changing its volume. We'll provide exact equations for each one of these deformations in the rest of this lecture. The first type of deformation that we want to discuss is tensile deformations. Tensile deformation occurs when length of an object changes in response to an applied force. Here we have a very specific scenario in mind. We're imagining a rod of initial length L sub I. The rod is fixed in place at one end, and a force F is applied to the other end of the rod. Notice that the force is being applied in a very specific direction. The force is being applied along the axis of the rod or parallel to the length of the rod. If this force were applied in a different direction, then we would get a different type of deformation. For example, if the force were applied perpendicular to the length of the rod, then we would get a bending of the rod. Here, since we're interested in tensile deformations, the force must be applied along the length of the rod. The rod does not have to be circular in cross-section. It could be rectangular in cross-section as shown here, or any other shape. What is important for us is the area of that cross-section. It's the area that essentially determines the thickness of the rod. In a typical deformation question, we're given the initial length of the rod, its cross-sectional area, and the applied force, and we're asked by how much does the rod stretch. In other words, we're interested in calculating delta L in terms of the other parameters provided here. The answer to that question lies in this equation. The change in the length of the rod is equal to the magnitude of the applied force times the initial length of the rod divided by the cross-sectional area divided by y. Y is the tensile modulus. It is also known as the Young's modulus for the material. Y measures the resistance of the material to tensile deformations. Roughly speaking, this parameter y basically tells us the type of material that we have. It essentially tells us how strong or how stiff the material is. Material scientists measure the Young's modulus for different types of materials, and the numbers are often provided in tables that you can find in your textbook. For example, rubber is relatively easy to stretch. The length of the rubber rod would be very easy to change by a large amount. Therefore, it has a relatively small Young's modulus. Its Young's modulus is 0.1 giganewtons per square meter. Steel, on the other hand, is a relatively strong material. It's difficult to stretch or change the length of a steel rod, so as you can see, its Young's modulus is a relatively large number. You don't really need to memorize any of these numbers, but given these numbers, you should be able to calculate the change in the length of the rod, given the force, its initial length, and the cross-sectional area. The second type of deformation that we want to discuss is shear deformations. Shear deformation occurs when parallel planes are shifted relative to each other. Once again, we have a very specific scenario in mind. So imagine a rectangular prism. This could be made of any material you want. Consider the top face and the bottom face of the prism, and imagine that two forces are applied to this object. Force F is parallel to the top face and to the right, and the second force is parallel to the bottom face and to the left. The two forces are equal in magnitude but opposite in direction. You can see that the net force on this object would be 0 when these are the only two forces acting on it. So the object overall will not accelerate to the left or to the right. However, it will change its shape. This specific type of change in shape, this specific type of deformation, is referred to as shear deformation. We can see that the prism is changing its shape because the top face of the prism moves relative to the bottom face. The amount that it moves by is delta x, and we're often interested in knowing exactly what delta x is. In other words, we want to know the displacement of the top face relative to the bottom face, and that quantity is provided by this formula. Delta x, the amount of shift between the two faces, is equal to the magnitude of the applied force times the initial height of the object, that refers to this dimension here, divided by the area, and that's the area of the top surface. So this area here is not a cross-sectional area. It's the area to which the force is applied. So the area of one face of this rectangular prism. All of that divided by S. S is the shear modulus. S measures the resistance of the material to shear deformations. Like Young's modulus, the shear modulus basically tells us how tough or strong the material is. However, the type of deformation that we're discussing here is a little bit different, so the shear modulus numerically would be different from the Young's modulus. The shear modulus of rubber is very, very small. Notice that its shear modulus is actually smaller than its tensile or Young's modulus. That basically indicates that it is easier to shear rubber than it is to stretch. As expected, materials like steel and tungsten have very high shear moduli because they're very strong, resistant materials. Again, you don't need to memorize any of these numbers, but given these numbers for a particular material, you should be able to calculate the amount of deformation. The third type of deformation that we want to discuss is bulk deformations. Bulk deformation occurs when the volume of an object changes in response to applied forces. Once again, we have a very specific scenario in mind. We're imagining a cube of initial volume V sub I, and we're imagining that 6 forces are applied to the 6 faces of this cube, and as a result, the volume changes by amount delta V. The 6 forces are all equal in magnitude, but of course they're pointing in different directions. Each force is perpendicular to the face that it's acting on. We're interested in knowing how much the volume changes in response to these 6 forces, and that answer is provided by this formula. The change in the volume of the cube is equal to the negative of the force being applied to one face of the cube times the initial volume of the cube divided by the area of one face of the cube divided by B. B is the bulk modulus. It measures the resistance of the material to bulk deformations. Once again, this modulus tells us how strong or how tough the material is. If you're trying to compress a block of tungsten, you'll have a very tough time at it. The volume would not change by very much because its bulk modulus is quite high. Here I've also listed the bulk modulus for diamond, which turns out to be even higher than tungsten. One of the reasons why diamond is considered one of the strongest or hardest materials in nature is exactly this number listed here. Notice that the formula for bulk deformations is different than the formulas for tensile or shear deformations in a couple of subtle ways. First of all, there is a negative sign in the formula here. The negative sign is basically telling us that the volume is decreasing or that the cube is shrinking in size. Remember that delta F is essentially V final minus V initial, so when delta V is a negative number, that tells us that the volume is decreasing, which is exactly what we expect to happen as a result of this scenario here. The other subtlety in this formula is that what we have here is not just F, but the change in force. It turns out under normal circumstances, any object on planet Earth is always subject to atmospheric pressure. So atmospheric pressure is constantly applying a force to every object on planet Earth. So every object on planet Earth, even as they sit there without any additional applied forces, they are already somewhat deformed in response to atmospheric forces. What we're interested in here is the additional deformation, the additional change in volume due to the additional applied force. So this delta F is the force that you or some machine would apply to the cube, and it does not include the natural, normal atmospheric forces that are always present. For that reason, this equation is often written in this form, where pressure is defined as force divided by area. So given one of these forces applied to one of these faces, F divided by A would give us the pressure acting on that face, and so delta F divided by A is often written as delta P, as in the additional change in pressure, not including atmospheric pressure. In this class, we've studied 3 very specific types of deformations. As you might imagine, there are many other types of deformations possible. We will not be discussing them further in this class, but I will say that any type of deformation always has an equation very similar to the 3 deformation equations you've seen so far. Every type of deformation that you could imagine has a modulus associated with it, a stress and a strain associated with it. The stress roughly describes the amount of force that you're applying to the object in order to deform it or change its geometry. The strain is the amount of deformation. In most problems, the strain is the thing that we want to calculate. It's how much the geometry actually changed when the stress was applied. And there's also the modulus, and the modulus is the thing that tells us how tough the material is, how resistant the substance is to deformations. And the relationship between these three quantities is expressed by this formula here. If you go back and look at the three formulas that we presented in this class, you see that they all fall into the same pattern. For each type of deformation, tensile, shear, or bulk, we had a certain type of modulus, the tensile or Young's modulus, the shear modulus, or the bulk modulus, and in each case the modulus was the ratio of a stress divided by a strain. The stress in the case of tensile deformations is force divided by area, and the strain is essentially the relative amount of stretching, so delta L divided by L initial. We didn't initially write the formula in this form, but of course if you rearrange this formula here, you'll get the formula that I presented to you a few slides ago. As I said, in this class we'll stay focused on tensile, shear, and bulk deformations, but it's nice to know that if at some point in your future you have to study different kinds of deformations like torsion or bending, the pattern that the equations follow will essentially be the same as the ones shown here. You may have noticed that in discussing our three types of deformations, the forces that were applied to the objects were always applied in specific directions and in a very specific manner. In particular, the applied forces always balanced each other. And you might be wondering what happens if the applied forces don't balance each other. For example, consider a rectangular prism, a block for example. Imagine that a force of 7 newtons is applied to the bottom face of the block, and a force of 10 newtons is applied to the top face of the block. Now, when we were talking about shear deformations earlier, we imagined that the top force and the bottom force are equal in magnitude. That's not what we have here. So you might be wondering, well, what happens in this case? It turns out this type of a scenario can be broken down into 3 scenarios that we have already discussed. For example, you could say that the net force on this block is going to be 3 newtons. That's 10 newtons minus 7 newtons. And this 3 newtons of force will cause the block to accelerate. So this block will begin to move to the right with a net force of 3 newtons. And of course, we know how to calculate the acceleration of the block. We can use Newton's second law of motion to figure out its acceleration and subsequent speed. But of course, in addition to accelerating to the right, the block will also deform, because in addition to this 3 newtons, there is a further 7 newtons that is being applied to the top face. That 7 newtons is balanced by the 7 newtons here. These 2 forces do not accelerate the block to the right. Instead, they deform the block, and we know how to calculate the deformation of the block. We've already seen equations for that. Of course, whenever you have forces being applied to an object like this, you could also have rotational motion. You can imagine that if you're pushing to the right on one side and pushing to the left on the other side, the entire block might begin to rotate around its center of mass. So we might also have angular motion, which is another thing we've studied in the past. So in the case of this unbalanced situation, what we get is a linear acceleration of the object. We can calculate that linear acceleration by calculating the net force and dividing by mass. We'll also get a shear deformation of the object, which we know how to calculate. And in addition to all that, we'll also get an angular acceleration alpha. To calculate that, we would have to figure out the torques that are acting on the object. We would have to know the moment of inertia of the object, and then we can calculate its angular acceleration. So if this block were an object floating in outer space and these two forces are applied to it, this block would have some very interesting behavior. It would begin to accelerate in one direction as it changes its shape while it rotates around its center of mass. These three types of motion are the three types that we have studied throughout the semester. You may have noticed that in our discussions of deformations, we always considered relatively simple geometric shapes. You might be wondering, what if the shape is unusual or simply more complicated than the cubes that we have been discussing? Well, for more complicated shapes, the shape can often be divided into small, simple shapes, which we can then separately analyze. For example, if you're trying to consider the tensile deformation of this rod here, you would notice that the rod does not have a uniform cross-section. You notice that the rod is thinner on one end and thicker on the other end. To deal with a situation like this, you would simply divide the rod into many, many small pieces. Then you could discuss the deformation of each small piece. Each small piece of this is essentially a nice rectangular piece. You can analyze that. You can figure out the change in its length. You can figure out the change in length for each piece and then add all of those together to get the total change in the length of this unusual looking rod. If you want to discuss, for example, the bulk deformation of a sphere, you could do a similar thing. You would divide the sphere into many, many small cubes, and the forces, if they are pointing in some awkward diagonal direction, they could be decomposed into horizontal and vertical forces. So, for example, this diagonal force can be viewed as the sum of two other forces, this vertical force and this horizontal force. Once again, a relatively complicated situation involving a sphere and diagonal forces can be reduced to basically a simple situation involving cubes and simple forces along the horizontal and vertical directions. One would then calculate the bulk deformation of each individual cube, add all of those changes in the volume together to find the net change in volume of the sphere. For more complicated shapes like a ceramic statue of an elephant, you would do the same thing, but here you might need a computer program to help you perform this type of analysis much more quickly. Engineers often do this, and the techniques that they use is referred to as finite element methods or finite element analysis. And that essentially refers to this idea of taking a complicated shape, dividing it into simple shapes that we can individually analyze, and then summing the result together to get the net change in the shape of the object. Although we will not be tested on finite element methods in this class, in case you're interested, I encourage you to watch this video for further information. Let's do a practice problem involving bulk deformations. Water pressure increases as depth increases. At the surface of a swimming pool where the pressure is 101,325 pascals, that's essentially atmospheric pressure, a beach ball has volume of 0.5 cubic meters. Suppose the ball is pushed underwater to a depth of 3 meters where the pressure is 130,725 pascals. What is the volume of the beach ball at that depth? The ball is filled with air, for which the bulk modulus is 1.4 times 10 to the fifth. So at the surface of the swimming pool where the beach ball is initially located, we have atmospheric pressure. Turns out atmospheric pressure is approximately 101,325 pascals. However, when this beach ball is pushed underwater, the pressure acting on it, and therefore the forces acting on it, will increase. And in this particular case, when the beach ball is pushed to a depth of 3 meters, the pressure acting on it will be approximately 130,725 pascals. This additional pressure or additional force will change the volume of the beach ball, so you should be thinking that the beach ball will shrink in volume. Once it's pushed underwater, its volume should be less than 0.5 cubic meters. We would like to know exactly what is that volume. Recall that the change in volume is equal to the negative of the change in pressure times the initial volume divided by the bulk modulus. The change in pressure can be found by essentially subtracting the initial pressure from the final pressure. The initial volume is 0.5 and the bulk modulus is given to us as 1.4 times 10 to the fifth. Plugging those numbers in, we will see that the volume of the beach ball will change by 0.105 cubic meters. The change is a negative change, meaning that the volume gets smaller. Notice that the question does not ask for the change in volume, but the actual volume of the beach ball. So now you need to add this number to the initial volume to find the final volume of the beach ball, and that will turn out to be 0.395 cubic meters. Let's solve a more challenging practice problem involving tensile deformations. A steel wire with length 2 meters and uniform circular cross-section of diameter 4 millimeters is placed over a light frictionless pulley. Masses of 5 kilograms and 3 kilograms are hung from the wire as shown. The masses are released and allowed to move freely. Compared to its length before attaching the objects, how much does the wire stretch while the objects are in motion? And the tensile modulus of steel is given to you. So you've seen problems involving pulleys several times before in chapters 5, 8, and 10, so you need to have some familiarity with the scenario described here. We have two objects, one of them M1 is clearly heavier than the other one, and so it will be falling and the other object will be rising. In this case, the pulley is assumed to be light and frictionless, so essentially we can ignore the mass or the moment of inertia of the pulley. That simplifies the analysis a little bit. As these masses accelerate, there will be some amount of tension in the rope. Tension, of course, is simply the force that's acting on the two ends of the rope, and this force will cause the rope to stretch. The rope will not stretch by very much, but there will be a slight deformation or stretching in the length of the rope. We would like to be able to calculate that. The first step in this problem is to figure out what the force is. Notice the force of tension in this problem is not even given to you. So maybe at this point you need to review some of the things that you learned in chapters 5, 8, and 10 in analyzing problems like this. And if you were to do that, you would find that the tension in the rope is given by this formula here. As it turns out, since the pulley is quote-unquote light, essentially massless, the tension on the two ends of the pulley will be equal to each other, and both will be given by this formula. We can plug numbers in and find that the tension is 36.75 newtons. Once we know the force that is being used to pull the steel wire, we can figure out how much it deforms by. Delta L, the change in length of the wire, is going to be the applied force, which is the tension we just calculated, times the initial length of the rope divided by the cross-sectional area. We can calculate that because we know that the diameter of the rope is 4 millimeters. Don't forget to convert that to SI units. And then, of course, the Young's modulus or the tensile modulus is given to us for steel. Plugging those numbers in, we'll see that this steel wire does not change in length by very much. The change in its length is only 0.0292 millimeters. I suppose the challenging part of this problem is really figuring out the tension. So on the next slide, we can go through the process of calculating the tension. So the main focus of this practice problem was really to calculate the change in the length of the steel wire, but of course that depended critically on what the tension in the wire was. It might be helpful for you to see in detail how the tension can be calculated. To begin with, we'll draw a force diagram. So we have several objects that we need to consider in this particular problem. We have mass M1, the forces acting on it are weight and tension 1. We have mass 2, and there are two forces acting on it. It's weight and tension 2. We also have the pulley. The pulley is being affected by the ropes, so we have tension 1 acting on the left side and tension 2 acting on the right side. The pulley might have its own mass, in which case it would have its own weight. So the force of gravity acting on the pulley would be mg. And then, of course, the pulley is presumably attached to the ceiling. It is somehow supported in place. So we would say that there's some kind of a support force holding it in place. We don't know what the exact nature of this support force is. For now, we're just calling it S. Once you've drawn a force diagram like the one here, it's good to adopt a standard coordinate system and then treat each mass separately. We'll begin with mass 1. We'll talk about the sum of the forces in the y direction. That ends up being T1 minus m1g. And according to Newton's second law of motion, the sum of the forces in the y direction should equal to mass times acceleration in the y direction. Since we have multiple masses, don't forget to label your masses carefully. This is m1 that we're talking about. Next, let's talk about m2. The sum of the forces in the y direction acting on the second object is T2 minus m2g, and that is equal to the mass of the second object times the acceleration of the second object in the y direction. We should also talk about the pulley just to be thorough. The net force acting on the pulley in the y direction is equal to the mysterious support force minus the weight of the pulley minus the two tensions that are pulling the pulley downwards. And that must equal to mass times acceleration of the pulley in the y direction. It's also useful to talk about torque. After all, as these masses m1 and m2 move up and down, the pulley is going to be rotating, and whenever you have rotational motion, it's a good idea to discuss torque. The net torque in the z direction will be the torque due to tension 1 minus the torque due to tension 2. Notice that the torque due to the weight of the pulley and the support force is going to be equal to 0 because the distance of those forces to the center of mass of the pulley is 0. And according to the angular version of the second law of motion, the net torque must equal to inertia times angular acceleration. Now note that we've been treating the problem quite generally. At this point, it's a good idea to point out that the pulley is not going to be falling. The pulley is supported securely in place, and so we're going to assume that the acceleration of the pulley in the y direction is 0. We're also going to assume that the rope does not stretch, at least not significantly. If it does stretch, it will do so throughout the length of the rope. And what that essentially means is that the acceleration of mass 1 must be equal to the acceleration of mass 2. More precisely, if mass 1 is accelerating downwards by some amount, mass 2 must be accelerating by exactly the same amount but in the opposite direction. So we can relate A1 and A2 very simply as follows. We should also mention that the rope does not slip on the pulley. So the pulley is not a slippery surface, for example. What that means is that as the rope moves up and down, there will always be a corresponding rotation of the pulley. If the pulley rotates, let's say, 1 full revolution, then the length of the rope that moves up or down must be equal to the circumference of the pulley. What that means is that there must be a connection between the linear motion and the angular motion. We can make that connection precise by saying that the linear acceleration is equal to the radius of the pulley times the angular acceleration of the pulley. Also, in the particular problem that we were discussing, the pulley was said to be light, effectively massless. So we can say that its moment of inertia is equal to 0. Remember that for a cylinder, the moment of inertia is 1/2 mr squared. If the pulley is quote-unquote light or it has negligible mass, its moment of inertia is going to be 0. When the moment of inertia is 0, that implies that the tensions acting on the two sides of the pulley must be equal to each other. So you could have assumed from the very beginning that T1 is equal to T2, but it's nice to see that this is really a consequence of the fact that the moment of inertia is equal to 0. Now we have all the pieces in place. We have our equations here near the top. and we can begin to solve for the unknowns. The two most interesting unknowns in this particular problem are the acceleration and the tension. Actually, we didn't really need the acceleration, but it's good to see that it can come out of this set of equations with a little bit of algebra. And the tension is exactly this equation, which is what we use to calculate the deformation of the steel wire on the previous slide. And that's the end of this lecture. Thank you for your attention.